So today we'll be talking about lifelong learning. I guess first logistics. The project milestones are due on Wednesday, and next week we have 2 guest lectures by Jeff Clune and Sergey Levin, and I highly encourage you to attend in person. I think that their talks will be pretty neat, talking about, I don't know the particular topic of Jeff's lecture yet, but it'll probably be covering things like evolutionary methods, more advanced topics in lifelong learning than the things that we'll be covering today, as well as other kind of interesting topics in the context of control, animation, evolution, those sorts of things. And then Sergey Levin will be talking about information theoretic exploration and unsupervised reinforcement learning and how that can be pertained to a form of like task agnostic reinforcement learning where you want to pre-train before knowing what task you're going to be doing. Okay, so the plan for today is we're going to be talking about lifelong learning. And before I go over the outline, I guess I'd like to preface this lecture by saying that in many ways lifelong learning I think is a very active area of research and a very open area of research. And I don't think that, as with a couple of the other lectures in this course, I think there may be more questions than answers. And so I'm going to try to have some interaction and some engagement with regard to some of those questions so that we can think about them in the lecture as well. So first we'll be talking about the lifelong learning problem statement. Then we'd be talking about some basic approaches to lifelong learning. And then we'll think about, can we do better than these basics? And we'll see 2 examples of ways that we can do better. And then revisit the problem statement of lifelong learning from the perspective of meta-learning. Okay, so let's first start by talking about the problem statement. And this is actually probably one of the biggest topics of the lecture, which is how do you actually formulate the problem of lifelong learning? And to review, the 2 main problem statements that we focused on in this course have been multitask learning and meta-learning, which may be in the context of supervised learning or reinforcement learning. And in multitask learning, the goal is to solve some set of tasks and then perform those tasks. And in meta-learning, the goal is to use experience from a set of tasks to be able to quickly learn a new task. And so the motivation behind things like lifelong learning is that in practice, unlike these problem statements, kind of the real world may look like something like this, where we don't have access to a set of tasks right off the bat, and instead we need to be learning in a more incremental or online fashion, where we are given objectives one at a time and we see data in a stream rather than in a batch. And so this is kind of a general temporal view of multitask learning or meta-learning is kind of what underpins the kind of idea behind things like lifelong learning. So some examples of this that I came up with, there are many other examples of lifelong learning systems that we may want to be able to create. So one example is a student learning concepts in school, learning, for example, math concepts ranging from simple addition to long division to algebra, calculus, etc. Another example might be, say you have some image classification system and you want to deploy it to help classify people's images for different users. And if it's deployed in the world, it will be seeing a stream of images and it will be given different tasks over time. And that may be a stationary distribution, it may be a non-stationary distribution because the world is changing and also the kinds of pictures that people take change over time. Another example is something like a robot acquiring an increasingly large set of skills in different environments. So in practice, we may want robots to do many different things, and we may not know right off the bat everything that we may want the robot to do. So instead, we want to kind of have this sequential setting. Also, in the context of language, you could imagine a virtual assistant helping different users with different tasks at different points in time, or something like a doctor's assistant aiding in medical decision-making decisions. In each of these cases, I guess, one of the key ideas behind lifelong learning is that when you deploy a machine learning system, it shouldn't be fixed. You shouldn't just kind of keep its weights the same and deploy it and run it. Instead, it should be continuing to learn based off of the data that it sees. And that will allow it to handle challenges relating to non-stationarity and challenges relating to it seeing tasks that it wasn't trained to do in the past. Okay. So with that in mind, first some terminology. So you can broadly view this class of problems as a form of sequential learning problem where you're given data, you're given tasks in sequence. But there are a lot of different terms that have been used to describe these kinds of sequential learning settings, ranging from things like online learning, lifelong learning, continual learning, incremental learning, streaming machine learning or streaming models or streaming data. I think all of these fall under the category of sequential learning. In general, the community doesn't use consistent terminology for many of these terms, unfortunately. So I think that I'll define a couple of these terms throughout the lecture, but otherwise, I think that when reading the literature, I wouldn't necessarily assume that these mean different things. They may all just mean the same thing. And that's a bit dissatisfying, I know, and then maybe in the future we can try to actually assign different names to these terms or better define the types of things that we're talking about. And it's also worth mentioning that this is distinct from sequence data. For example, something like language is a sequential form of data, but that doesn't mean that you're learning from it in sequence. You could still have a batch of sequential data that you're learning from. And likewise, this is also different from sequential decision-making. Things like reinforcement learning are a form of a sequential decision-making problem where the actions that you take at your current time step affect the next action. But you could also do sequential decision-making in a batch learning setting where you're just given one environment and one batch of data from that environment and you want to learn a policy. And so there's like three different forms of viewing sequential data, sequential decision-making, and sequential learning. And in this lecture, we'll be focusing on sequential learning. Okay, any questions? Okay, so I want to do a little exercise. So I don't think that there's really, as I kind of alluded to before, I don't think there's necessarily any consensus to what the lifelong learning problem statement is. And I think that actually in many different contexts, it will vary based off of the things that you care about in that application. And so what I'd like to do in the next, 5 to 10 minutes is have each of you pick an example problem setting from the example problem settings that I showed on the previous slide, and I'll bring them back up again. And maybe also pair up with someone or form a group of 2 or 3 and discuss the problem statement corresponding to that problem setting with your partner. And in particular, try to answer the questions such as, how would you set up an experiment in order to develop and test your algorithm? And this will kind of help you identify the sort of actual underlying problem statement underlying that example. What are desirable or required properties of the algorithm as they pertain to different things like memory, privacy, data, those sorts of things? What things do you want out of your algorithm in that problem setting? And then also, how do you evaluate a system? So if you have an algorithm that can solve the lifelong learning problem, how do you actually go about evaluating whether or not it's doing a good job or doing a bad job? Okay, so here are the example settings that I showed on the previous slide. If you want, you can also come up with a new example setting if you're feeling creative. And I'll give you a few minutes to chat with someone else in the room about these problem statements. Ready, go. Oh, and then afterwards, I'm going to ask you guys to say what you discussed and what was specific to that problem setting.
I mean, I guess I was thinking about just to contrive games. Get one target game, it's just you get a stream of the target game. You might get an even target game. Maybe that's too late.
Yeah, no, I think what would be one thing you don't want to lifelong learning, you don't want to forget things. Sure. Right, so you can end the set up in some way. Estimate how much you might forget. You can forget all of the stuff. Yeah. Just after you would have some sort of side goals.
Well, I think one of the things as kids, you're saying you don't want to degrade performance. Yeah, you have G1. We are more brilliant as kids, but I was we say go. Get better. You can get better at those.
Oh, I see. Sort of maybe code
Well, I mean, I guess like one is
Okay, are we ready to regroup? Or do you need another minute? Raise your hand if you think you need another minute.
Yeah, sure.
Okay, let's regroup, and you guys can think. I'll go visit you guys last. Okay, so let's start with this group right here. So which examples did you pick, and what were your considerations for A, B, and C?
So we picked the example of student learning concepts in school, and then in terms of an experiment, we kind of divided it into two sections. So one, the student would need to be able to learn new concepts without forgetting old ones. Mm-hmm. So kind of eliminate or reduce negative transfer.
Okay, so like negative backward transfer.
Yeah.
Okay. So this is for A. You can keep on talking.
Exactly. So that when they they learn a new task and forget an old one, then the other property would be that they can as well generate new tasks, and we said as well with increasing complexity to sort of challenge themselves to kind of push themselves and learn something new based on some given input.
Cool. So like an ability to generate new tasks.
Yeah.
And how would you evaluate that ability?
So in terms of experiment and testing, so we're thinking about, so we have a sequence of tasks with increasing complexity.
Okay. Cool. Yeah. So the experimental set would have like increasingly difficult tasks.
We weren't sure exactly how to encoding like the task generation with some latent distribution, and then maybe measuring like the entropy of that distribution and trying to kind of like increase that from task to task.
Okay, so yeah, seeing if it can generate a broader range of tasks. And you probably want something in addition to just entropy of that task distribution, maybe also something relating to whether or not they're solvable tasks or something. Okay, cool. Anything else to add?
So maybe the algorithm doesn't have to remember everything from the beginning, just the memory consideration.
Right. So you're saying that maybe you don't need to, maybe it's okay to forget some things?
Yeah.
Okay. Cool. Okay, next group.
Oh, we also take that first.
Okay.
So pretty similar, but one thing on top of it is instead of have a predefined like path of curriculum, you might want to kind of sample the path so it's kind of clear distribution of paths of a lot of paths, and you might want to kind of test or evaluate the algorithm with respect to different paths.
Okay, so you're saying that basically you want to maintain a distribution over all of your previous tasks and evaluate it on all of the previous tasks?
Yeah.
Okay, cool. I'll put that under evaluation. And then the second point was maybe maybe you don't care about all of the past tasks, but just a subset of them or a certain distribution over them. Yeah, okay, cool. Anything that was different from the first group that you felt like wasn't important?
So one thing I'm not sure is, should we kind of predefine the kind of the dependencies of all those tasks, or is like a thing that you can learn?
Yeah, so like where does the curriculum of tasks come from?
Right.
Yeah, that's a good question. I guess I don't really have a box for that, but yeah, that's good. Okay, next group.
So we looked at example C.
Okay.
In particular, we'd be interested in having sort of an agent that develops a large library of tasks that at the same time are as sort of abstract as possible, so they can kind of apply the maximal number of problems in the distribution, hopefully without having negative transfer effects. We were also thinking a lot about how this might potentially have to be evaluated with a certain kind of curriculum in mind in terms of which sort of problems are presented to the robot as time passes, because that might severely influence which kinds of skills get acquired over time.
I see. So you're thinking about both, like how the evaluation is kind of intermixed into the learning process itself. Yeah. Okay. Cool. I feel like that's mostly covered about all the things up here,
Yeah.
more or less. Okay. Was there anything else? Krishna?
So maybe like, I guess the desirable required properties of the algorithm is like, you don't want to have negative transfer and you want to be able to generate new tasks, but maybe like in terms of like the training scheme that you use, like one desired property from that would be related to this curriculum thing is that you need to be, like if you were to try to evaluate, like list sort of like a discrete set of like properties that you want, properties for the tasks and then properties related to like the environments, then you want to be able to like take sort of the combinatorial combinations of like all the different possible tasks you could have in different environments, and then that could be used to kind of construct your evaluation set. And you want to be kind of, you want to assume that maybe like when you're evaluating that you can take any combination of these tasks and environments and be able to like generate a new task instance that you work on. So it's kind of like robust to all possible combinations of tasks and environments and like the combinations that you could have there.
So like evaluating on held out combinations of like tasks, environments, variations on the tasks.
Yeah.
Okay. Yeah.
Pertaining to the increasingly large set of skills part of C, it probably is important that the skills be parameterized in a continuous fashion rather than a discrete way, since it's already known that that's going to cause natural branching that we have.
Yeah, so like a continuous parameterization of tasks. Okay, the group in the middle.
We talked about E, having a doctor's assistant.
Okay.
So we talked about a couple things that came up, but one like more specific example is like diagnosing like the flu, for example. If you had a stream of patients coming into your office and you wanted to know if this new patient based on their symptoms has the flu or doesn't. So there was like still want the algorithm to perform well no matter like what time of year it is.
Mm-hmm.
And you also want it to be able to remember information from many years past, because maybe flu strains, there's like different ones with slightly different symptoms. And you want it to do well on the new patients that you get, as opposed to maybe the previous ones that you've seen. You want it to like mostly do well on the like new patients that
Yeah, so you want some sort of kind of memory of the past, and also you may have like periodic signals like seasons, for example, and you want to be able to take that into account in your decision making to perform well. I guess in addition to transfer and generating new tasks, there's also just generally like good performance is something that we care about. Yeah.
performance, I think Gina was mentioning maybe the active learning could be a good feature to have, because oftentimes assistant will recommend a further check to doctor, and the doctor or panel of doctors give it, learning skills. So having that active learning could be potentially ideal for when the assistant was not sure.
Yeah. And that's particularly relevant if you're seeing like out of distribution data, for example. Yeah.
So one question that I had is basically like, what sequence does the task come in? Do you learn the easier task first, or do you learn the harder task first? So that's why what's possible when you evaluate how successful you are.
Yeah, so considering like different sequences of tasks. And you want it to be potentially robust to those different types of sequences if you're in a medical decision-making situation, because you don't know if you're going to be seeing easier cases to harder cases, or if you may see some intermixing of hard cases and easy cases. Great. Okay. The group in the back.
So we talked about D, virtual assistant, and I guess we were talking about kind of like two different spectrums here. Like one spectrum was like on the one side, we don't want to bias like towards a single set of users or single set of tasks at a single set of time. But then on the other hand, maybe, for example, if you're seeing this single task a lot more frequently towards like recent times, maybe the virtual assistant should focus on learning that task as compared to others. So we were like kind of like asking about how we should balance those two between like biasing towards a set of groups and better not to. And in terms of evaluation, we also talked about how the performance on different tasks could be different depending on which training point we look at. And that was also an interesting question, because at different checkpoints within a training period, we might want to focus on different tasks. We might want to evaluate on different tasks. So we were just like talking about this.
Yeah, that's a good point. Like if there's one user that you've been repeatedly seeing a lot and very recently, then you may want to like focus some of your representational capacity on that user, because it's likely that in the near future you'll see them again, and you want to be able to make good decisions then. Great. Group in the middle.
So I guess we talked about something closer to A. In particular, we talked about how young children as they grow up, they have like very broad but like very few categories of classifying things. So they can classify birds and they can classify like animals. And as they grow up, they acquire more and more categories at a finer grade levels. And we talked about potentially lifelong learning system around that, and in particular there are some papers in neuroscience showing that if you break a hierarchical data set into several hierarchies, that as the learning process evolves, the latent activations of classes evolve along the hierarchical tree.
So like a course-defined type approach?
Yeah, and we talked about how you would potentially want a system like that has introduced finer grained classes, and as the training goes faster and faster, you want to potentially be able to learn these finer grained classes faster and faster, based on the previous sort of classification.
Right, so you might have a kind of course-defined type of tasks, and you care about like learning efficiency, like being able to learn more quickly as you see new concepts in sequence. I'm not sure if course-defined falls under evaluation or properties, but I think that this kind of gray area is what makes these sorts of problems interesting. This group?
So I think we basically talk about B. We're considering a sequential learning for image classification systems. For example, at the first stage, user provide a data set of handwritten digits. So basically, we want the system to be able to identify different digits. And at the second stage, later in time, the user may provide the data set of ImageNet. So basically, we want the system to be able to do classification on the ImageNet, on the natural images. So this would be like a sequential learning of different classification data sets.
Mm-hmm.
In terms of the property, I think we discussed, first of all, we want the system to be able to adapt to the new data set faster than training from scratch. And also things, more likely the training will be in a sequential way. So which probably can lead to like some catastrophic forgetting problem. So the system may forget what it learned previously. So we don't want that to happen. So we want the system can basically continuously learning and building up the knowledge across different tasks.
So we'd want to test on old tasks in addition to fresh new tasks.
Yeah. So yeah, like evaluation on like this is like a mixture of tasks.
One kind of new thing though that we talked about is the idea of maybe having it classify things that we don't specify at all. So I mean I don't think it's really the way, but having it like if we were to show it images of cats, like even have it somehow sub-classify those cats, and create classifications that we don't specify, that it just kind of hands us these fresh, unsupervised classes.
Yeah, so kind of like maybe generation of new tasks, but from unlabeled data.
Yeah. Exactly.
Yeah.
I think another thing is, I think as we mentioned, we basically need to keep all the data from previous tasks during the evaluation stage. I think it would be, ideally, it would be to remove keeping, increasing the data as we, encountering different tasks over time. So we don't want to keep all the previous data sets.
So like O of n memory.
Yeah.
Like little o of n.
Yeah.
Memory.
Yeah, ideally, yeah.
Yeah. Okay, and then last group.
So one idea in the student learning context in school is, if we didn't say this, we want the student to have some introspective capabilities. Like they should know that, oh, I'm not good at this task.
Yeah.
Not only so they can focus on learning that task, but also sort of so they don't go on American Idol if they suck at singing. Like it's good. That's very useful, right?
I'm going to put this next to active learning because it relates pretty closely to like understanding when you should ask for more information.
Yeah, because I feel like there's two aspects. One is, what are you good at, and what should you practice on? And the other one was, I think this was said sort of, what are actually, if you're a student in school, you can't learn everything, focus on things that will be useful later.
Yeah.
Perhaps in the case of students, you could imagine money, how much will you make, or like that could be a signal of what are the things you learned actually useful if you actually get paid later on when you use them.
Great.
Just something when we were talking about that I was thinking about is, wouldn't it be good for the model to be able to expand its parameter set and its architecture, so not have a fixed?
Yeah.
If you're getting increasingly complicated tasks over time.
So like a dynamic architecture capacity.
Yeah.
Okay. Krishna, did you have a comment?
Yeah, I guess this is kind of like related to some of the things that were written down, but in the evaluation side of things, it would be useful to, I think, have a good understanding of like what the trade-off is between generalization and specialization for this algorithm, where like on one hand, like if you're trying to get it to work better on like increasingly difficult tasks and you want it to kind of get specialized, then maybe your weight is more heavily on that like component of like the that evaluation metric. And then at the same time, if you want it to be able to like the robot to be able to adapt to like cleaning a bunch of different houses, and it's okay if initially it doesn't perform that well at cleaning a new house because it's just kind of like learning to adapt to that new house, then you kind of want it to be more of a generalist and you want it to be focused on like the variety of like different houses as opposed to how
Yeah, and I also suspect that something like generalization versus specialization is going to be something application dependent. Like in many situations, you may care about like it being like very consistently performing very well in the situations where you really need it to perform well, versus being able to do something like do more things but slightly at a lower degree of performance, like a robot doing things with like a lower success rate or like more slowly than if it were a specialist that was specifically tuned for doing one particular task. Yeah.
Yeah, one thought I also had was, perhaps this is more down the line, but perhaps we want to make sure that they don't, like the agent doesn't learn dangerous things. Like in the case of student, we don't want the student going on like a website, have to build weapons and things like that. So you could imagine like if they have just a large pool of tasks that they end up learning things that we don't want them to learn.
Right, so when they propose their own tasks, they should propose things that are useful and ethical.
Yeah.
Okay, great. I think that was a great discussion. And I think that, I guess one takeaway from this is I think that in different applications you care about different things. Like in some applications you really want it to kind of remember everything and be able to perform well in a wide variety of situations. Whereas in other applications you care a lot more about just the recent thing and the things that it needs to do now. So for example, in a decision-making situation, you don't want it to forget past events and want to be able to recognize new trends when they're happening, whereas in a student learning concepts in school, maybe they don't need to, maybe if they're not using very basic long division skills, maybe they don't need to remember those long division skills because they're not actually useful for their current position. So I don't know if I personally don't use long division a lot, so I think it's okay if I forget that particular skill, for example. Okay. Okay, so let's I wrote out some problem variations and evaluation considerations on the slide, just to kind of, and I think that we probably covered most of the things here, but we can go over some of these things. So one variation is how the tasks come to the agent. So we talked about this a little bit. They may come in a curriculum from easy to hard, or they may be more something like IID, where you see both a range of difficult tasks and hard and easy tasks in some sort of stream. There's also a setting called predictable, which is a general, it's a less strong notion of IID. It's similar to the seasons, for example. If you know it's kind of the end of summer, you know that fall is likely to come, and so you can see that sort of trend in your stream of data. And then there's also, I don't think it was covered in any of these settings, but there's also settings where you have adversarial tasks coming in, and that might be if you have a competitive environment and you're trying to learn how to I don't know, compete against another agent, then the types of tasks that may be coming in are going to be tasks that are particularly targeted towards the types of tasks that you do poorly at. And so that's also a variation of the lifelong learning problem statement. And the type of algorithm that you develop may be very much influenced by these different types of categories. Another variation of the problems is whether or not you have very discrete task boundaries or more continuous task boundaries. This came up when we were talking about having kind of your task be continuously parameterized versus having more discrete tasks. And then there's also situations where you know where the task boundaries are and where you don't know the task boundaries are. So for example, if you're in grade school, if you're going from first grade to second grade, or you're given one problem versus another problem, there's pretty clear shifts. But if you are diagnosing flu symptoms or making diagnosis for the flu, you may not know shifts in the data distribution that you're seeing. Do you have a question? No. Okay, cool. Some considerations in terms of like the desirable properties that we care about. Model performance, as we discussed, data efficiency, the ability to learn new things quickly. We didn't really talk about this, but computational resources, and this is actually going to come up a fair amount in thinking about the algorithms that we develop. And it's related to this memory, but in terms of computation. You don't want the computation to grow grow linearly in n, for example, as you see more tasks. And then there's other considerations such as privacy, interpretability, fairness, and the amount of compute and memory you use at test time. Some of these things are things that you care about in standard machine learning settings and aren't specific to lifelong learning. Although one thing that comes up that we'll touch on in a couple slides is privacy. If you're in the medical decision-making setting, for example, it may not be, you may not be allowed to actually store all of the data perpetually, and so that may motivate settings where you have to store things in the memory of the neural network rather than storing them in plain text. Although in that setting, it's unclear if you're storing things in the weights of a neural network. Maybe you're still storing them, and maybe that's also violating privacy, patient privacy. So some kind of interesting philosophical questions there. Yeah, so in general, substantial variety in the problem statement, and unfortunately, all of these generally fall under the umbrella of lifelong learning or online learning, and so it makes it rather difficult a bit to tease apart some of the different advances in this area. Okay, so now let's look at one very concrete instantiation of the lifelong learning problem statement, and this typically falls under what's called online learning, and it's very simple. So you have time that's passing, and you observe an input. You make a prediction about the label corresponding to that input, and then you observe the label for that input. And then the loop iterates. So this is basically vanilla online learning. And in the very general case, you could make no assumptions about what X is and what Y is. And also, in the general case, you could just you could not place any restrictions on memory, on computation, and just want to be able to solve this problem in the general case. So that's the most general formulation of the problem. You may make some certain assumptions. So one assumption that you can make is that the data is coming in IID. So the xt is drawn from p of x, and yt is drawn from p of y given x. And note that p is not a function of t, so it's a stationary distribution. This is one example of online learning, and this assumption can make it easier to think about algorithms, even if the data density doesn't necessarily follow these assumptions. Otherwise, if you assume that you're not in the IID setting, then you assume some sort of time-varying distribution over x and y given x. And there's other, as I alluded to before, there's also a setting called the predictable setting that I don't have text for, but that's the setting where you can actually predict something about the next distribution based off of the trends you've seen in the past. Okay, so another assumption or another consideration or restriction that you can put on this is what I'm going to call the streaming setting. And in this setting, you can't store xt and yt. You can only look at them once, and then you're kind of given the next thing. You're not allowed to have any memory. And so this could be very useful if you're in settings where you don't have any memory, or just the amount of data, the quantity of data is so enormous that it's impractical to think about storing it due to memory or due to computational resources. So if you have streaming video, for example, every single second, it may be impractical to store that. It could also relate to privacy considerations, as I mentioned before. And it could also relate to wanting to study neural memory mechanisms. So there's a kind of a subfield of lifelong learning that really cares about how humans remember things when they're given a stream of data. And so if you care about kind of this biologically plausible form of memory that is more biologically plausible than like a hard drive, then you could consider this setting. And it's worth mentioning that this is certainly true in some cases that you cannot store x and y, but in many cases, it is actually practical to store the data that you're seeing. We have very large data sets like ImageNet. We have pretty big hard drives. And so from a practical point of view, it can be actually very sensible to store the data that you're seeing for a range of problem settings. So for example, in reinforcement learning settings, we store our data in replay buffers, and we typically replay that data to the agent in order to allow it to continuously learn from that data. Okay, and then the last variation on this problem statement that I had written down is that if you know where the task boundaries are, you may also be observing some task descriptor ZT that could correspond to a one-hot vector or some other more descriptive description of the task. And in that case, you would observe both XT as well as the task descriptor. Although you could also put this into the general case of online learning where XT contains both the input and the task descriptor. Okay, so this is the problem statement, or several different variations on a general problem statement. Now, what do you want from your lifelong learning algorithm? And in particular, how do you go about evaluating lifelong learning algorithms? There are two metrics that or two classes of metrics that I think are useful for thinking about this. And I don't think anyone really gave a concrete metric when we were discussing this before. So let's talk about that now. One of the most classic metrics in online learning is what's called regret. And you want to have minimal regret, and you want your regret to grow slowly with the time. And in particular, what regret refers to is the cumulative loss of the learner. So essentially the integral of the loss for each of the data points that you see, subtracted by the cumulative loss of the best learner in hindsight. So this is basically a comparison between your cumulative loss and what you could have done in the best case. And mathematically, what this looks like is the following. So say theta t is the parameters that you choose at each time step to make predictions. The cumulative regret of the cumulative loss of yourself is the left term, where you're just adding up the loss for the set of parameters that you used at each time step. And the right term is referring to, in hindsight, if you had some model that minimized the loss for those time steps, basically kind of the best set of parameters that you could have done or that you could have used to perform that sequence of tasks. Okay, yeah. Yeah, so this cannot be evaluated in practice, typically, but it's very useful for analysis. And in particular, for thinking about in simplified settings, usually in convex settings, can we study how the regret grows for these algorithms? So one thing worth noting is that regret that grows linearly in T is trivial to obtain. Can anyone tell me why that is the case?
Just have an algorithm return a random result, a random action in the reinforcement learning setting, or random prediction. But does it depend on data?
Let's see. So if you output kind of a random parameter vector, it would grow linearly in T. You could actually do slightly better than that and still have it be linear. Are there any other? So that's a good example. Are there any other examples of where you could get a learner that is linear in T? Yeah?
You could just keep data fixed.
Mm-hmm. So if you keep theta fixed at like a random initialization?
Yeah, or even like at any performance.
At any performance. What do you mean?
Like theta t for any t, then if you just return the same loss, it will always be linear. What was that?
Right, so you don't get to choose the loss. You only get to choose theta.
Right, but at each epoch, then you'll have the same loss for a given theta.
If you keep theta fixed, you won't necessarily have the same loss for all of the tasks. Does that make sense?
Yeah.
Although if you have a random theta, you would guess that you would probably have a similar loss for all the tasks. I guess the same thing for fixed. Any other thoughts? Yeah.
Could you do that every t, have the data that just minimizes the loss of that t?
Yeah. So if you just train from scratch on each of the t tasks and disregard any previous experience, then you would get linear regret because the loss, or assuming that the tasks are of a similar difficulty, if you just train on each of those tasks from scratch, you would get linear regret, and because the loss value would be constant, and so the loss would increase. And so in practice, what we typically want is sublinear growth in your regret so that you can actually use your previous experience to do better on the future tasks. Okay. Cool, so that's one metric that's used typically in the online learning literature, and in practice, as I mentioned, it's something that's very difficult to evaluate. So let's think about some metrics that we could actually evaluate in practice. And so I think the most common metric that people use in lifelong learning is thinking about positive and negative transfer. So I guess first you can look at performance on your set of tasks, but in addition to performance, you could look at how well your tasks are allowing you to perform other tasks. And so particular positive forward transfer refers to a setting where previous tasks can cause you to do better on future tasks compared to learning the future tasks from scratch. So if you basically compare how well you do on future tasks after learning the previous tasks compared to learning future tasks from scratch, that can give you a measure of positive transfer. And positive backward transfer would be if a current task allows you to do better on previous tasks. And this would be compared to learning those past tasks from scratch before seeing your current task. And then if you want to define negative transfer, just replace the word better with the word worse, and you'll get negative transfer. If basically previous tasks cause you to do worse on future tasks, and if current tasks allow you to do, or cause you to do worse on previous tasks. Okay. So this is a metric that can allow us to study whether or not lifelong learning is allowing us to learn well. Yeah?
Is it symmetrical? So let's say I have two tasks A and B. So I learn A first and I learn B, and I say that B is a positive backward transfer. So in that case, if I learn B first and I learn A, is it the same as saying that there's a positive forward transfer?
Right, so typically it's not a symmetric metric. For example, if you learn how to, what's an example of this? If you learn how to grasp objects, and then you learn how to grasp an object and put it into a container, if you learn the grasping thing first and then the container thing, then you'll be faster at learning the task of picking and placing if you have a good learner. Whereas if you reverse the order, you learn how to kind of pick and place, and then you learn how to grasp. The time it will take to learn how to grasp should be trivial after learning how to pick and place. And so basically, if you flip the order of those two tasks, for one of them, you get positive forward transfer to some degree, and the other order, you get positive forward transfer to a much greater degree if you have a good learner. Does that answer your question? Okay. And that's something that's interesting and worth keeping in mind as you think about, and it can be useful for thinking about how do you actually order the tasks. Okay, so now that we've spent a long time on the problem statement, let's actually talk about some approaches for solving it. And we can start with the very basic approaches. So, and by basic, I mean really the most naive things you could imagine doing. So the first approach you could imagine doing under settings where you don't have a lot of constraints on what you're allowed to do with the data is just store all the data that you've seen so far and train on it until you achieve the optimal loss function for all the data that you've seen. And this actually has a name to it, so it's called the follow the leader algorithm. And it's actually, if you have the ability to do this, then this is an extremely strong approach. Basically saying, given all the data that you've seen so far, train on it and minimize the loss on all that data. And it will achieve very strong performance because you won't necessarily overfit to the most recent data because you'll be continuously training on everything. Yeah. The downsides is that it's very computationally intensive. So if at every single time you see a new data point, you now train on everything you've seen, then your training time is actually worse than O of n because as you see more data, you'll presumably have to do more computation. That said, if you kind of continuously fine-tune instead of trying to train from scratch at every time step, you instead kind of fine-tune from what you learned before, then it may actually be more practical to do this. It can also be memory intensive. So if you're in applications where you can't store all the data you've seen, then this is a problem. If you're in applications where you can store all the data, this is fine. So this depends on the application. Okay. Second naive approach that you could imagine doing is, particularly if you're in a setting where you can't store data, you could just imagine taking a gradient step on the data point that you observe. And this corresponds to stochastic gradient descent, as many of us should all know, and what you've been using in your homework. This is very computationally cheap. It requires no memory. And the downside is that it's subject to negative backward transfer if the data points that it sees do not kind of cover the things that it saw previously. And this is what is known as forgetting, sometimes also referred to as catastrophic forgetting. How catastrophic it is depends on the application that you're in. So maybe it's fine that you forgot how to do long division, for example. That's really not a catastrophe, but maybe in other settings, if you forget how to make decisions based on a current season, then that is potentially more catastrophic. Yeah?
So to avoid catastrophic forgetting in the first setting, you have to always be randomizing like how you sample the next match.
Yeah, so the way that the first setting avoids forgetting is that it just stores all the data that it's seen and continuously replays that data and continuously trains on that data.
But not in any fixed order.
Right, yeah, so the top version will, in principle, the follow the leader algorithm will actually train to convergence on all of the data that you've seen so far, where you store the data and you sample it IID from your buffer of data. Yeah?
So when you talk about like strong performance, is this with respect to regret or something else?
It's with respect to something like regret, and in convex settings under certain, I think, smoothness assumptions and convexity assumptions, and maybe actually be strong convexity, you can show that it gets O of log n regret. And log n is pretty good. Yeah.
And so, does this not work so well if you assume that like maybe there are a lot of local minima that you can converge to when you're training the sort of leader on all of the data all at once? And are there any cases where like training on less data can actually give you a better get you a better leader performance?
So for the first question, if you are continuously fine-tuning, then like it could certainly be the case that at the beginning you get to a certain place in your optimization landscape from training on a very small amount of data that is very hard to get out of. And there's actually some interesting work by Stefano Soato that looks at these sorts of critical periods in neural network training and how that affects training in later parts of training. And that's actually, that will hurt potentially both of these two approaches because you could overfit to small amounts of data or get to a bad part of the optimization landscape. And so one way to do that is just to restart, like randomly initialize your network at different points during training. And in principle, like on paper, the follow the leader algorithm will do that. At every single time step, will reinitialize your neural network. If you want to implement it in practice, you would probably want to do some sort of continuous fine-tuning or periodic random initializations. What was your second question?
I guess it was just about like if sometimes using like a smaller subset of the data as opposed to all of the data up until the point that you've like trained is in some ways like better to train the leader. Like if you, for example, like if you selectively choose examples that are more instructive and leave out examples that are either redundant or actually might hurt the performance because let's say you collect way too many negative examples and you want to somehow balance like positive and negative examples while training your leader or something like that.
Yeah, so in general, I think, yeah, in general in machine learning, not just in lifelong learning, the distribution of the data that you're training on matters. And so, for example, if you have a highly imbalanced classification task where you have, maybe you're actually like doing medical diagnosis and like 99% of your people, of your patients don't have the condition and 1% do, then rebalancing that a little bit can actually help you get better performance. And then also in reinforcement learning contexts, for example, if the data that you're seeing is highly imbalanced, then it could be that you could do better by rebalancing it in different ways. Typically, you don't rebalance by using less data. Typically, you rebalance by just sampling the data in a different manner. In general, I don't think there is that much that is known about how best to optimally balance your data. And I think that typically it depends on the types of data that you're seeing at test time. I mean, in practice, you want the balance to be the same as what you're going to be seeing at test time. OK. Oh, the other thing, the other note or other downside of SGD is that it is a somewhat slow learning process. And so, and that's why we typically replay our data multiple times and do multiple epochs of training. And that's because SGD doesn't update as quickly as possible if you just give it one pass through of the data. And so we may want algorithms that can learn faster. OK. So the next question is, can we do better? So these are the two basics, I think, two most basic algorithms in online learning and continual learning. And so I'll cover a couple algorithms that allow us to do better than these algorithms in different problem settings. So the first case study that we'll look at is, if SGD is slow, can we use meta-learning to make it faster in online learning problem settings? And so in particular, what we're going to do is we'll revisit the example that we saw in the last lecture, where we have some agent that is learning to traverse different terrains. And at different points in time, it sees different terrains. Remember that we talked about how this form of online adaptation can be viewed as a form of few-shot learning, where the tasks are different temporal slices of your experience. But now what's going to be different this time is we're going to consider a setting where we see a new terrain, and we see data from that new terrain. And that setting might be extrapolated from the kinds of things that we learned before. And so this is going to be an example of an online learning problem where we continuously see data from that terrain, and we want to be able to eventually learn how to handle that terrain. And so because it's extrapolated from what we saw before, if we just take the last k time steps of experience, that isn't going to be sufficient to learn to adapt to an entirely new terrain. So how do we solve this problem? One option would be to continuously run SGD. So basically, take the SGD algorithm that I talked about before, and just for each window of k time steps, you take another gradient step. And this will do better than taking one gradient step on the last k. And it will be pretty fast with a manual initialization. The downside is, though, that if you see ice for a while, you adapt to that by running SGD. And then you go back to one of your other terrains. If you've adapted your parameter vector and specialized it for ice, then you may not be able to do well on other terrains, and you may also forget the meta-learned initialization that allowed you to adapt very quickly in the first place. OK, so how could we do better than SGD in this setting? I guess the first thing worth noting is that we can do better by meta training with a manual initialization that will allow us to adapt more quickly. But we can also do better than that and try to solve the second problem. So we can view this as a form of online inference. So at each point in time, we want to be able to identify the task that we're in. And we may not be able to observe that task. So for example, when we're on ice, we may not be able to observe that we're on ice. And when we move back to another terrain, we need to be able to infer from the data that we're on a new terrain. So what we'll do, in this case, task is corresponding to the terrain that we're on, or the model, the dynamics model that we're under. And it may not correspond to a semantic task that you're trying to accomplish. OK, so we want to be able to infer the terrain or the task at each time step. And once we do that, what we're going to do is we're going to have a mixture model of parameters, one for each of the tasks that we have. And once we infer the task that we're in, we can then just run the parameters corresponding to that task for planning. So in particular, we'll have a mixture of neural network parameters over your task variable. And for each of those mixture components, we'll take an SGD step on that component when we think that we're in that data regime. So you can actually formulate this as an expectation maximization problem, where the E step is going to correspond to estimating which terrain you're on or which task you're in, given your data. So let's say that let's just kind of simplify the notation and say that the last k time steps of data, S and A, is just going to correspond to xt and yt for a given time step. And the way that we can estimate which task we're in will look like this. So we want to be able to estimate the probability that we're in task I, given the data at the current time step. And so what we'll do is we'll multiply the likelihood of the data under each of the tasks. So imagine that we're under task I, look at the likelihood of being under task I, and then we'll multiply that by the prior that we're in task I. So this can tell us basically the probability that the current terrain corresponds to a particular task. Okay, so once we have a set of parameters, once we've identified which task we're in, we can then update the parameters corresponding to that task by just taking an SGD step. And we can do that actually in a soft way. So we can have these probabilities be continuous probabilities, and then we'll take a gradient step. So we'll have a parameter vector for each task, and then we'll take a gradient descent step that is on each mixture element weighted by the probability of the task. So this is just the probability of the task right here, and we'll take a gradient step on the data that we observed for that task. So if this probability is 0, if we're not in that terrain, we won't update the parameters for that task or that terrain. And if we are in that terrain, for example, if the probability is 1 or very high, then we'll take a gradient step using that data. Any questions on how this works? Yeah? Yeah, so this is a good question. So what we did for that is you can basically allow it to instantiate new tasks. And basically allow it to incrementally grow the number of tasks that it sees. And in particular, what you can use is you can use something called a Chinese restaurant process prior that corresponds to the prior probability that you're in a new situation or in a new task or a new terrain. And then if you think that the probability, so there'll be a probability of being under any of the terrains that you've seen previously, and there will also be a probability of being in a new terrain. And to evaluate that probability, we'll have the prior term corresponding to the Chinese restaurant process prior, and then we'll also have the likelihood of the data. If you reinitialize to the meta-learned initialization to the prior, take one gradient step on that terrain and see the likelihood of how well that explains the data versus all the other tasks. One downside is that you may add a lot of tasks. And so at some point, you may need to refresh the tasks or kind of remove the tasks that you haven't seen recently. Yeah?
Kind of like a follow-up question. So it sounds like very similar to topic modeling, that you don't know how many topics up ahead, like then you decided whatever Dirichlet prior or some transfer route process stuff. But the likelihood that you maximize doesn't necessarily serve the potential probability that you adapt the new terrain that you're going to see. So how are you evaluating the successfulness of like entering into the right trace or right path for your robot in this case?
So you're asking how do you evaluate, so it's definitely similar to topic modeling and like Dirichlet processes. You're asking how do you evaluate whether or not you are in, like whether or not a task corresponds to a terrain?
Yeah, or how can you tell this path is successful if you don't train or see this topic in your training set, and you like arbitrarily assign this new topic to the new data that you came across, and how are you able to tell this new topic you haven't came across before is the right new topic for your context in this terrain setting? Like the evaluation is kind of still mysterious.
Yeah, so we are given both, like at each time step we are given, we're doing like model-based reinforcement learning, so we're learning a dynamics model. And so we have actually the labels, which is basically the next state. And so that can tell us that can allow us to explain whether or not, to identify whether or not a given point in our data stream corresponds to a certain model by looking at the likelihood of that data under our model. In terms of identifying whether or not you're in a kind of one of the tasks that you've seen previously versus a new task, you can basically, for a new task, you can just reset to your meta-learned initialization and take one gradient step and see if that explains the data better, if that gives a higher likelihood on the data compared to the other parameter vectors that you have. Does that answer your question? Okay. Yeah.
So, and I think I've asked that question on that lecture a couple weeks ago, but what's your opinion on this? What is the benefit of maintaining multiple models versus online system identification?
Yeah, so in this setting, so this is maintaining multiple models. It's maintaining like a mixture model of models. One of the benefits that you get is that you can, with multiple models, you can potentially adapt in 0 shot or in like 1 shot. Like once you basically see a data point, you can use that to identify which model you should use. Whereas a form of kind of online system identification needs to actually adapt using that data from a prior. And it may be that you need more than one data point to adapt. So the recall is essentially can be faster if you are maintaining multiple models compared to having a single prior. The benefit of using a prior is that you don't have to maintain multiple sets of parameters. And so that can also be nice. Does that answer your question?
Yeah.
Okay. Yeah.
So when you're evaluating and you're giving it like, so let's say a completely new terrain, and you're not allowed to like fine tune on that new terrain, does it basically learn to like mix the models that it's learned for the over the distribution of terrains that it's learned up to that point to kind of like, I don't know, average its behavior on this new terrain? Is that kind of what it does, or?
So we do allow it to continuously fine tune on as it sees data. And so if it sees a terrain that is like that is very different from anything that it saw before, then it will instantiate a new task or a new model for that. If it seems to be like a mixture of 2 terrains, and those 2 terrains explain, like a mixture of those 2 terrains, basically a linear mixture explains the data well, then it will use both of those. It will use a linear combination of those parameters, and then it will update both of them with a gradient step that's weighted by 1/2. It'll update each model by 1/2 the strength. Yeah.
Is the mammal or meta-learned initialization, did you do that before starting this algorithm, or did you also update it concurrently?
Yeah, that's a good question. So in this case, the initialization is pre-trained, and that's done just like ahead of time, and then you run this form of online learning from that initialization. One really important thing to think about is, can you then take that data and use that to improve your initialization? For example, if you start seeing ice, you should then kind of incorporate that into your prior such that you improve your prior, and maybe you can kind of discard the ice model, as was alluded to before, and just adapt to that from your prior. But you can't do that until you actually start incorporating data into it. This work didn't study that setting, and I guess one of the challenges that's worth thinking about is, can you instead, like, adaptation is very fast because it's meta-trained for fast adaptation. But if you do an update to the meta-learned parameters, that update won't necessarily be fast. That will be like a slow update, and so it may not be able to actually incorporate that data or a small amount of that data to change the prior very quickly. You could imagine a form of like meta-learning such that you train it also such that the updates to the meta-learned model are also fast, but that would be tricky. Okay. And along those lines, one of the things worth noting is that if your neural network is randomly initialized and you do this procedure, it wouldn't work that well because the adaptation steps won't be very fast, and you won't be able to adapt very far to your to those new terrains or those new situations that you're in. So having some sort of meta-learned initialization is very important for successful online learning. Okay. So this is one approach for using meta-learning to make online learning faster and also being able to alleviate the forgetting problem. I'll quickly run through a couple of the experiments that actually looked at how this works in practice. So in this case, the experiments looked at 2 different settings at test time. One setting where the legs or the creature, I think it was called a crawler, was in a constant crippled setting, versus the second setting was one where there was regions of flipping between the legs being crippled or being disabled and the legs being fixed. And then the y-axis is going to show the reward that's normalized based off of the performance of all the methods in each of the 2 situations. And then there's different methods that we can compare. So the first thing that we can do is online learning with the mammal initialization, as we described on the previous slide. You could also do a mammal initialization, but just run SGD. And this will do well at continuously adapting, but may forget and may kind of specialize too much. You could also do the original approach of just always resetting to your prior and taking 1 gradient step at every single time step. This will allow you to adapt quickly, but won't necessarily allow you to accumulate data if you're in a setting that's extrapolated. And then the last 2 examples are non-meta learning approaches that either don't do adaptation and just try to learn a single model, or learn a model and fine-tune that model with gradient descent steps, but those gradient descent steps may not be very fast. So a lot of different methods. In the constant crippled setting, we don't really expect to see much difference between these kinds of approaches because you can fit a single model to that setting, and you don't really need to. It's okay to kind of continuously just keep on running SGD steps, and so we see the methods do somewhat similarly. Whereas if we have these regions of the legs being crippled versus the legs not being crippled, first, meta learning is very important to actually be able to adapt to these different settings. So we see a big difference between the first 3 approaches and the second 2. And also we see that using always resetting and running SGD continuously don't perform well because they aren't able to accumulate data and also very quickly switch between these modes. And so that's why we see the green doing better than the red and the blue. And then the other thing that you can look at is the task distribution that's learned, and it's kind of identifying which mixture elements to use at which points in time. And so what you can see is that in this case, the tasks were switching every 500 steps, and it learns that in these increments, it learns to use these tasks. So from 500 to 1,000 and from 1,500 to 2,000, it always identifies it very clearly as task 1 or model number 1. And in the other increments, it seems to prefer using the task with ID of 1. Sorry, the first case it was task ID 2, and then the second one it seems to prefer task ID 1, and it ends up specializing that model to the terrain as it sees more data on that terrain or in that situation. Okay. Any questions? Yeah.
Were there any experiments where it needed to like use 3 at once, like a mixture of 3 different tasks at one environment?
So in these, I guess it's choosing how many models it wants to use.
Actually, yeah, between 1,000 and 1,500, there's like green, red.
There's a little bit of green, yeah. So it is choosing in some degree to use 3 models. I think it's mostly dominated by 1 and 3 though, rather than 2. Okay. So now I'd like to talk about a second case study, which is what if we're not in the meta learning setting and we don't have a way to pre-train for initialization that's very fast? Can we modify vanilla SGD to avoid negative backward transfer when we're learning from scratch? And there's been actually a fairly large amount of work in this area, and I'm going to highlight one work that I think considers a fairly principled approach to this problem. And that was some work by David Lopez-Paz and Mark Aurelio Ranzado called Gradient Episodic Memory for Continual Learning. And the key idea behind this approach is that you can first store some amount of data per task in memory, but only store a small amount of data in contrast to storing everything. and you have actually a fixed memory size. And then when making updates for new tasks, ensure that the updates that you make don't unlearn your previous tasks. And I guess the second idea is, or the second concept is what most methods are trying to do, what most methods in continual learning are trying to do. So the key lies in how do we actually try to accomplish two. And what this approach is going to do is it's going to try to leverage the small amount of data that's stored in memory to ensure that future updates don't hurt the previous tasks that are stored, and by using the data that's stored in memory. Okay, so let's say that our predictor is parameterized by or is f theta, and it knows the input and the task corresponds to zt. And then we'll have some memory corresponding to mk for task k, or for task dk. What this approach will do is for every time step, it's going to take an update step on the data point xt, yt with respect to the predictor, subject to the constraint that the loss on the stored data points in memory doesn't get worse than it was for the previous model. And it's going to do this for all of the tasks stored, all the tasks that were previously seen. So this seems pretty reasonable. We basically just want to ensure that the loss function doesn't go down for those tasks, and we're going to be using the data points in a more weak way than if we're going to try to directly train on them. The challenge with this is that it's hard to think about how you'd actually solve this constrained optimization problem. And so one of the things that was neat in this paper is they showed that, they came up with the idea that if you assume local linearity of the optimization landscape, then you can basically use the gradient of the task to rephrase this constrained. Yeah?
Do you update the memory in this case, or is it a static distribution?
Right, sorry, I guess I didn't put this in here. But yeah, you also update the memory at each time step and store a set of data points for each task that you see. And the memory storing mechanism that you used in this paper was quite simple. They just took the total size of the memory, divided it by the total number of tasks, and then for each task they saw, they just added that number of data points to the memory, such that it kind of filled the max capacity. But I think that more sophisticated approaches would also probably do better. Okay, so if you assume linearity or local linearity of the optimization landscape, then you can actually rephrase the second constraint as saying that you want the inner product between the gradient that you take with respect to your current data point and the gradient of the data points in your memory to be non-negative. And this is basically saying that when you apply the gradient on your current time step, or basically apply GT, you want GT to not go in the opposite direction as the gradients for all of your other tasks. And if it points in the same direction as those tasks, then it will, well, if it's orthogonal, then, and the space is locally linear, then it will keep the loss the same for all of those previous tasks. And if it actually points in the same direction and has a positive inner product, then, and the space is locally linear, then you'll actually get positive backward transfer. It'll actually improve those previous tasks. The other assumption that this makes is that the small amount of data stored in your memory is representative of those previous tasks. Okay, and then what you can do is you can replace this, the constraint there with the constraint there, and you can then formulate this as a quadratic program and use QP solvers to figure out how to modify your gradient such that the constraints are satisfied. Great. So in their experiments, they looked at a few different problems. They looked at permutations of MNIST, where the pixels were permuted, and you saw a sequence of tasks corresponding to different permutations of the pixels. They also looked at rotated MNIST digits, same thing, but rotating the pixels. and also CFAR 100, where it introduces 5 classes of CFAR for each task. And they evaluated backward transfer as well as forward transfer, as well as the accuracy on each of the tasks in sequence. And the total memory size that they used was 5,000 examples across all of the tasks. Okay, so here are what the results look like. So you can see that in general, so GEM is what this method is called. It was able to achieve higher accuracy than training a single model on everything, and in compared to training independent models on each of the tasks. And if you look at what the right plot is showing, is it's showing the performance of the models as you add more and more tasks. And it's showing, I think, the performance of the first task after seeing each sequence of tasks. And you can see that it doesn't, for many of the methods, it starts to decline due to negative backward transfer. Whereas for this approach, it's able to maintain a high accuracy even as you see more data. And you can see fairly consistent trends for the other approaches as well, or the other benchmarks. One thing that I'd like to note here is if you take a step back and think about this experimental setup, you might think, well, do these experimental domains make sense for studying problems in backward transfer and forgetting? And if you're in a setting where you have 20 MNIST tasks or 20 CFAR 100 tasks, those are both settings where it's actually very easy to store the entire data set in your replay buffer or on your hard drive. And so they aren't necessarily reflective of the kinds of problems that we care about in lifelong learning where we can't store data. And so an approach where you just store everything and train on it would actually probably do much better than all the approaches pictured. So something to keep in mind when you're developing algorithms. There's also some algorithms that kind of combine the ideas of these two approaches where we actually try to meta-learn how to avoid negative backward transfer. There's a paper at NeurIPS that is covering that. And because we're out of time, I'll jump ahead to, I'll skip, the last part was about online meta-learning, which we don't have time to cover. The main takeaways that I want to get across is that there are many flavors of lifelong learning that are all under the same name. Defining the problem statement is often the hardest part, and it varies based off of what you care about in your particular application. And also, in many ways, meta-learning, where you try to actually optimize for fast learning, can be viewed as a slice of the lifelong learning problem, where you want, if you really care about positive forward transfer and data efficiency. And lastly, it's a very open and active area of research. Okay, a couple of reminders again. Project milestones are due on Wednesday, and 2 guest lectures next week, Jeff Clune and Sergey Levin. I'll see you next week, or on Wednesday.